Imagine we have some data set with many features, with hundreds of thousands, and we cannot look at it because a plot has 2 or 3 axes, but we have hundreds. But all those features are connected, they move together, so the data doesn't fill all directions. And therefore, we're trying to find the way to describe all the data with fewer number of features without significant loss of the variance. That's why we need PCA, and I will show you how it's done under the hood from the scratch, and after that, how it's done in the proper way. So let's build some small data set. That's how it looks like. And as you can see, the shape of the data is long in the one direction and thin in another. Now the goal is to find the direction in which the data varies along most. And those directions are called principal components. So the recipe looks like that. First of all, we need to move the cloud to the original coordinate system. After that, we measure how it spreads. And after that, just rid of those directions of the largest spread. To the center, we need to find the mean of every feature of our data set. And after that, we just subtract it from every row. It looks like that. Geometrically, it equals to shifting the cloud to the original coordinate system. Let me remind you two quantities we use to describe the shape of the data. And please notice we have the center data. So the first one is variance, which is just an average of sum of squared centered components of that feature. And the second one is covariance, which tell us how two features are moving together. And actually the variance is the same covariance, just like a feature with itself. And as I said, covariance is reading how two features moving together. And as you can see for our example, both coordinates are above average or both are below. So the product is positive. And doing the same for every point, we can see that 8 out of the 10 products are positive. So the covariance comes out positive, which means features are moving in the same direction. Like when the first feature is increased, the second is going to be increased as well. Now let's multiply the table data by itself. And as you can see, it creates new matrix whose elements looks very the same as the variance and covariance we had. So on the diagonal, we can see almost the variance equations if we divide them by the number of observations. And off-diagonal elements are covariances if we divide them by the number of observations as well. So let's divide them. And this division creates a new matrix called covariance matrix. And this covariance matrix is everything we know about how the cloud is spread. Other steps are very similar to what SVD does. Therefore, I recommend you to watch my previous video about that. So let's take some direction, which is a vector, and project every observation onto that direction. To do that, we just multiply our data matrix with that vector on the right. And therefore, we have a new vector whose components are coordinates of our observations on that new direction. And such as data matrix X is centered, its mean is equal to 0. And now we can calculate the variance of the data in that direction. And such as data is centered, we just have an average of squared each component, which in matrix form can be represented as following. And as you can see, this part in the brackets is our covariance matrix. And therefore, we can say that the variance of this new vector can be represented as that with the covariance matrix. And we can estimate every new direction with this number. And as I said, we are trying to find the direction with the largest spread. Therefore, the first vector, the first principal component, is unit direction, unit vector with the largest variance. So we can run the search just by rotating the unit vector and write down all the variance values. And after that, just selecting the direction with the highest variance. And this new vector is the direction on which the data has the largest variance. But this approach, where we just sweep in all the direction, is not an algorithm, because for 2 features we have only one angle to try, but for 3 features it's a sphere of directions, and for n features in n-1 dimensional sphere. So we need to find the answer directly, not by trying all possible directions. And that's what the SVD gives us. So let me remind you that SVD of the center table can be revealed as following with these 3 matrices. And by the way, if we call some SVD function in the numpy, we're going to return us these 3 matrices. Where the first matrix on the right is the matrix with all the directions we need. It contains vectors which are that is sorted by the variance value and are perpendicular to each other. And the second sigma matrix contains something similar to the variance I will show you later. Therefore, we need just to conduct this SVD decomposition instead of the manual search. So as I said, matrix V holds the directions as the columns, and the first column is the strongest vector, meaning the vector with the strongest variance. So it looks like that if we just extract these two vectors. And now we can represent our data points in the coordinate system of those two vectors, which are our new axes. So to find the coordinates of each data point in that new coordinate system, we just need to multiply the data matrix with new V matrix. So the same cloud is now read on new axis and looks like that. So now we can move forward dimensionality reduction. And this matrix V has a number of vectors equal to the number of features, which is dimensionality of X data matrix from which this matrix was calculated. And therefore, if we need to reduce dimensionality, we just need to keep only the first k directions, first k vectors of this matrix, and multiply the data matrix with this truncated matrix V. So imagine we have a data set with 3 features, meaning that every observation now has 3 numbers. And we can see the clouds is kind of flat, meaning that it's spread mostly only in the 2 directions, and the third one is almost nothing. And it means we can reduce dimensionality to remove that third direction, meaning that all these data points are going to be projected onto the plane, because 2 directions, we create new coordinate system, which is 2-dimensional, so it's a plane, and those points are going to be projected on that plane. The second matrix the SVD returns is sigma matrix, and it contains singular values on the diagonal. And those sigma values are actually square root of eigenvalues of normalized matrix. So we can extract the eigenvalues by just taking an average of squared singular values. And we know from the eigenvector definition that the variance of the data matrix along the eigenvector is equal to the eigenvalue. This is the SVD video to understand it better. And if we divide this eigenvalue of one direction with the sum of all the eigenvalues, we can find the share of the spread that one component carries. For example, if the first component share 90% of the spread, it means that almost all the data, like 90% of the data, is spread out onto that direction. So let's move back to the cloud we flattened with the 3 features, and suppose we extracted values like that. It means that the third component we found, the first vector, contains 80% of the total spread, the second component 18%, and the last one less than 1%. So if we reduce dimensionality and remove the third component, we're going to have 99.4% of the spread saved, meaning we lost only 0.6. And we can do the same, for example, for some data set with 30 features, we can analyze and find that if we keep the 5 components, it's going to save us almost 97% of features. So we can remove the rest 25 features and lose only 3% of the variance. So the smaller this number k is, the fewer features we keep and more spread is thrown away. And the larger k is, the closer to the original data we are. But what if we want going back to the original space? To do that, we just need to take that matrix, which is our data matrix in this new projected space, and multiply it with the V matrix again. And as the mean, we subtract it to center the data. But the problem is that it doesn't undo the reduction, and the variance that was dropped is gone. Example, if we have 2 features in the PCA space, and we do this going back step, the source coordinate is 0. So let's do that on our example with 3 features. After this step, every point now has 3 coordinates, but they never leave the plane PC1 and PC2 component span, because the third coordinate is equal to 0, and we cannot put back the third direction. One important thing to keep in mind, sometimes a feature with larger units takes over others, like in this example. And if it is a PCA, the data is not going to be changed because the first component explains almost all the variance. And that's why we need to standardize the columns, just by subtracting its mean and divided by the standard deviation. After this step, units don't matter, and as you can see, you see one component it has completely different direction than it had before. So we do standardization when the features are in different units and no scale is more meaningful than another. But we can leave it alone when every feature is already in the same unit or the spread itself carries some information. Let's look at an example with the images. So one image is one row of the dataset, and every pixel position is a feature, so the dataset has 784 features, and we stock together 10,000 of images. And if we apply SVD on the dataset, it's gonna return us matrix V, where each vector has the same dimensionality as the dataset, meaning 784. And if we calculate the mean of the dataset, it looks like that, just some average of all images. And if we move backward or forward along that first PCA vector, for example, the image is going to be changed like that. So the picture is changed in one coherent way. And if we apply PCA on that dataset, we can see that 50 components is enough to clearly differ the digits. But it's better to apply PCA not on one image, because that way the patterns belong only to the picture alone, but to the whole dataset of images. So the patterns are shared by every image in the set. So a new image can be given coordinates in the same 50 directions all the image in the dataset had. Let's look at another example. So suppose we trained some multi-class classification model to recognize different digits on 3,000 digits. And this model returns something called embeddings. In another case, let it be 512 numbers. And we stock these embeddings into a table for all the training set. And now we need to feed PCA on that whole table once. So we find the mean of embeddings and apply SVD to find the shared directions of the training set. And in result, we have one coordinate system that every embedding can be read in. And this approach helps us to understand what models see, such as all the digits from the training set are in one coordinate system. And as you can see, it's easy to differ different classes in this three-dimensional space. Now look straight on the third axis when we just reduce dimensionality to the components. And as you can see, digits classes 4 and 5 sit on top of each other. And when we turn it back to three components, the third axis pulls them apart. So when we had two components, the gap between classes 4 and 5 was 0.7. But when we add the third component, the gap increased to 6.6. So if we see some overlap of two classes on our plane, it's not necessarily means that the model cannot differ those classes, because this overlap was in the picture, not in the data. So PCA lets us to look at the structure the model learned, but overlapping the picture is not evidence that the embeddings are inseparable, and few directions cannot hold everything. 512 of them do, so a projection can hide a difference. So the core idea is that we have one feed which are used everywhere. We feed in the training or some reference sets and reuse the same mean and those same directions everywhere, and never feed again per image or per split or per batch, because different feeds give us different coordinate systems and nothing is comparable.